Okay, so step 7, enforce the boundary conditions in the NHD, the non-homogeneous direction. Again, this is our problem, restated exactly as it was. We've assembled the solutions. Temperature is the sum of all these terms, and now we need to enforce dt dy at y equals 0, and t at y equals h is equal to th. So let's see, how do we do this? Let's start with boundary condition. Let's call this one 1. Let's call this one 2. Let's start with boundary condition 1 at y equals 0. So we're going to say my partial with respect to y at y equals 0 is equal to, so we're just evaluating this. Let's see, what are we doing? The derivative of this function. So that's going to be the sum over all I. I'll just leave it as shorthand, sum over I. Sine of lambda I x. Now evaluating this, right? By the way, sine of lambda I x, differential with respect to y, is just that term back, right? That's not affected. But the stuff inside the brackets is. So we have C3I times, the derivative is now lambda I comes out, and we have sinh of lambda I times 0 plus C4I lambda I cosh of lambda I times 0. And that all has to equal 0. Right, that's just evaluating that derivative. Okay, what can we do? We know that the sinh of 0, this term here, that is 0. We know that cosh is 1. So this is actually telling us that, let's walk through this step here. So this is telling us dt, dy at y equals 0 is equal to the sum over all I of sine lambda I x C3I, I'm sorry, what was it, C4I, lambda I sine of lambda I x, oops, sinh, right? Wait, hold on, what are we doing here? Nope, that's 1. Sorry, let me make sure I get this right. C4I lambda I sine lambda x equals 0. Somebody tell me if I messed that up. So sine, the lambda C4 comes over here, equals 0. I think that's right. So it's telling us that. Again, what we're trying to do is enforce the boundary condition so that we can figure out how to solve for these constants here, C4I. So this kind of helps us, like it gets rid of some of this stuff, but we still have this function of x, and we're going to have to deal with that. But let's maybe note here that the only thing that can force this function to be true is you pick some value of x, lambda we know is not 0, sine of that value is probably not 0. So lambda is not 0. That means C4, for this, any of these to be true, C4I, every single one of them has to be 0. So this boundary condition is helping us by telling us C4I has to be 0 for every value of I. So that's good. All right, that means we can simplify our equation down a little bit, and we end up with restating the full solution is just t sum of I C3I cosh lambda I y times sine of lambda I x. Right? C3I. So now we actually only have one set of unknown coefficients left. But it's infinitely many unknown coefficients, which is still a problem. But we'll figure out how to deal with that. So let's now attempt the second boundary condition. So second boundary condition here says what? It says that this function, the temperature function, evaluated at y equals h, is equal to th. So let's evaluate this function. It's the sum of c. So now that we only have one set of coefficients, I'm just going to call it ci. Right, so I'm saying c3i is just ci now. Yeah.
Did we have a C1i when we evaluated dx?
Yes, but it was, so we had C1 up here and C3 and C4, but we don't know what these coefficients are. It's like it doesn't, we don't have a specification for them yet, so we can just lump C1 in with the others. So an unknown coefficient out here times unknown coefficients here is unknown coefficient, so it falls in. Okay, but we end up with this single set Ci of unknown coefficients times now cosh of lambda I. So we're evaluating this at h, y equals h. And then we have sine lambda I still as at x. So again, for the third time, we have an infinitely many number of unknown coefficients. And we need to solve for that. The tricky part is we've evaluated the boundary condition in x, so we have no more boundary conditions to deal with for x, yet we still have a function that depends on x in our evaluation of the boundary condition for y, right? Here we don't have any y anymore, but we still have a functional dependence on x. So how are we going to deal with this, right? We need some way to solve for those unknown coefficients ci. And again, those coefficients, those end up being the ones that are scaling our sine functions that we end up adding back together. So, okay, what we need to do now is use a special property of this of these functions that are called orthogonality. Right? Orthogonality sounds scary if you've had calc before. You probably are like, oh God, but it's not that bad, right? It's a really kind of simple idea. The main idea is as follows. Let me just write this out here. We're going to use orthogonality of the eigenfunctions. And that is saying the following, that in general, if I take the definite integral from homogeneous boundary condition 1 to homogeneous boundary condition 2, so this would be in the x direction for this problem. So I'm going to go from 0 to w, but just in general, you go from 1 to 2, and I take the product of some eigenfunction at index I, and the same eigenfunction at index j, right, with respect to whatever the variable is. So we'll call that s. Here it's x. I'm taking the integral, the definite integral of these two different instances of the same eigenfunction. That tells us the following. That's going to tell us it's either 0 if I is not equal to j, or, sorry, it's not 0 if I equals j. So hopefully that's clear. Think about that for a second. Maybe it will help to have a specific example, but we'll get there in a second. So what it's saying is, right, for my problem over here, tx, c1 sine of lambda x, that's my eigenfunction. So if I take sine of lambda I and then sine of lambda j x, multiply those two functions together, integrate over the definite integral, it's 0 if I and j are not the same index. Right? And that's something that honestly you could stare at for months and try to understand and see where it's coming from. But maybe it also helps to look at these examples. So just to prove this is something I was a little skeptical of, right? Or why this works. It works because if you have the eigenvalues chosen carefully and the periods line up in a certain way, and you take specific examples of these functions, it actually does do as follows. So here we have this example. This is a sine function. So I'm taking lambda at I equals 1. That's my blue line. So this is the start of the sine function. And then I have lambda at I equals 2. That's this one here. The green is the product of the two functions. And I go through and numerically integrate the green line, right, from 0 to 1, which is the boundary that I chose. You can see, well, you can't see, but what it says here is the result of that integral is 3.5 something times 10 to the minus 16th. Okay, so it's 0, right? So we prove for this one. You could do the same thing. So here I equals 1 for the blue, I equals 9 for the orange, and then the green is the product of the two. Again, it's something times 10 to the minus 18. This one is now, I'm taking I equals 3 for both, okay, blue and orange, so it's the same function. Multiply that together, that gives you the green. That is now 0.5, right? That's my integral. So this, at least by example, proves the idea that this property is true. If you wanted to, I generated these plots and put the Python function in the lecture notes, and you could go back and prove to yourself or your very skeptical roommate or something that this is true. So, okay, so this is orthogonality. So we're going to use this. Right? We're going to use this to help us solve for these constants. For our specific example, it looks like the following. We're going to take the integral from 0 to w of sine lambda I x times sine of lambda j times x with respect to dx. And we're going to expect that to be 0 if I is not equal to j, not 0 if I does equal j. Right, that's for this example. And where did I get sine? Sine is the eigenfunction. It's the solution to my homogeneous problem. Right, it's the kernel of the function there, that sine part of the tx. Yeah?
But what exactly is j? So we're summing over I, but now all of a sudden we have another j.
So what I'm saying here is we have an infinite series of eigenvalues, right? If I take any two eigenvalues in that infinite series and multiply them together, the only time that they're going to not equal 0 is if those are the same I and j, if I and j are the same. So at this point, we're not doing a summation over I or anything. I'm just using those indices to indicate this is one position in the series and this is another position in the series.
So I and j belong to the same domain?
Yes. They would be within the set of whatever indices go with this particular eigenvalue set. Yeah?
And then, is this a test or is this actually plotting something physical? Like these plots on the bottom, what's the y?
Yeah, so this is the eigenfunction here. It's just sine of lambda x for this problem, where lambda, I think I chose it so that it went from 0, the domain went from 0 to 1 as opposed to 0 to w. But it's just plotting the sine function and then multiplying them together for this. So it's essentially a test of this property in a numerical setting. So I know it's kind of a cool property that arises and not something you expect, but really at the core what it's saying in orthogonality is, in general, what orthogonality tells you is that the information that is provided by one thing is independent from the information that's provided by another thing. Right? That's what orthogonality is telling you. So if you have like a coordinate system, and the coordinates have to be orthogonal, they're telling you different things about the same system. And that's what this is telling you.